All right, let's get started. So we've got another back-to-back homework situation here, but this time it's separated by a weekend, which makes it hopefully a little bit simpler than this week where you had an assignment due on Tuesday and then one due today. In Chapter 6, it was another situation of a really long assignment that I snipped up into two parts to try and make a little bit more manageable. So homework 6A will be due on Thursday the 9th, which is a week from today, and then 6B will be due the Tuesday following that. Now also, on Tuesday, November 14th, we're going to have our second midterm exam. And you'll still have access to that same equation sheet that I posted on MU Online and that you used during the first exam. So if you want to start familiarizing yourself with what's available for the second exam, you can do that. The exam coverage is Chapter 4, 5, and 6. And so the main ideas in Chapter 4 are local acceleration versus convective acceleration. Remember Bernoulli's equation, Euler's equation, rotational flow. Those are the key ideas in Chapter 4. Chapter 5, which we just finished, is continuity relationship, and then combining continuity with other things like Bernoulli's equation or manometers, those combination problems. And then Chapter 6, which we're going to be beginning today, is all about fluid momentum. So it's an important section of the course. I just got a question before class about the final exam, and the question was, is the final exam cumulative? And the answer is kinda. It would be impossible to give a non-cumulative exam in this course just because the concepts really do sequentially build on each other. So, for instance, you have to know about fluid properties to do momentum problems, even though we're not specifically talking about with the focus on fluid properties, we're still going to use that information in Chapter 6. And so likewise, when we move past Exam 2 and we're picking up the energy equation in Chapter 7, you're still going to have to know principles like continuity relationship and the energy equation, Bernoulli's equation. So the final exam will be focused on the material since Exam 2, but there will be a need for you to still understand the older material just because it all sort of fits together. So that's a long-winded way of saying sort of. It's sort of cumulative. All right, so any questions about these announcements before we start on Chapter 6? All right, I want to show you a video of a jet boots paired with a wingsuit. Sounds pretty exciting, right? It's a great video. I just wish it was a higher resolution. This is actually more than 10 years old now, but still worth watching. Oh, let me do this. Turn on the audio and pause the recording. He was successful in that one, but who knows where he's at today. So we're going to be talking about momentum. And in that case, what he was able to do was translate the kerosene that was in those bladders that he was, the blue rubberized containers he was tucking into his suit. Seems a little dangerous, right, to be tucking kerosene into your suit there. So I got into some of the numbers there, and it turns out that each one of those boots generates 16 kilograms of thrust. And the way that they would start it up was it was a mixture of butane and propane to prime the jets, and those were basically hobby engines that people would put into like a remote controlled airplane. You know, they're remote controlled jets, and so he had one of them connected to each boot, and then it was burning about half a liter per minute on each one of those jets. So the jump was originally from 7,000 feet, and he did maintain horizontal flight. It was kind of hard to understand what we was saying at the end there, but when I was reading a description of it, he tried to actually climb and gain some altitude, but it stalled. Those wingsuits aren't designed for lift so much as to try and give you a little bit of forward movement as you're falling downward. So kind of an interesting project and a good introduction to the ideas of momentum. Let's look at the derivation of the momentum equation as we're going to be using it in Chapter 6. And it starts off with Newton's second law. And so we all know that when there is a certain mass that's being accelerated, that we have to apply a force in order to cause that acceleration. And so the way that we could describe this is that the sum of the forces that are acting on a body result on its acceleration. Now, what we're going to do is put in the substitution instead of just calling it A for our acceleration. What we mean specifically is local acceleration, or the change in velocity over time of some particle. And so again, we're saying that some particle is changing velocity over time, and we apply a force to that mass in order to achieve the change in velocity over time. Now, we can move the mass term on the inside of this derivative, and when we have m times v, that's the definition that we're going to use of momentum. And so momentum is some mass multiplied by the velocity that it's experiencing. And if we have a continuously connected body of particles, then we're going to call that our system. The system, rather than just a single particle, it can be like a stream of fluid. And so what this is saying now is that the change of momentum in a system over time is due to an imbalanced force being applied to it. So in the case of those jet boots, what was happening is that you're having combustion inside of the jet chamber, where it's taking in oxygen, it's burning the kerosene, and the exhaust is going out. And as a result of that really high velocity exhaust that's going out, then it's applying a force to the boots. Now, momentum is the product of mass and velocity. So if you want a lot of mass, if you want a lot of momentum, because you're trying to maximize the force that those boots can apply, you either have to have really high velocities or a lot of mass. And so the mass that was available was partially limited by the fuel that he's carrying inside of those blue rubberized bladders. Now, that's not all of the mass, though, because, of course, combustion is using atmospheric gases as well. So the kerosene that's being burned is just part of the mass stream that's going out of those jet boots. But in order to generate the thrust, the strategy that they were using was to maximize the velocity, because the mass flow rate itself was kind of limited by the fuel that's available. And that same factor is true in most aircraft, where they're trying to reduce how much fuel has to be carried up in the plane, and so they're trying to make the jet engines maximize the velocity in order to get as much force as possible. Okay, so remember Reynolds transport theorem, and that says that we're going to be looking at accumulation of something inside of the control volume and flow of things through the control surface. Now, in this case, what we're going to be saying is that we could look at the flow of momentum through control surfaces, because here on the inside of this integral, what we've got is the velocity of the fluid, density, velocity, and area. And so density, velocity, and area together is the mass flow rate. Remember that mass flow rate, m dot, is density times q, and we know that q is VA. So mass flow rate is the density, velocity, and some cross-sectional area. So that if we have momentum being m times v, then the inside of this term, this first velocity is the velocity of the stream of fluid, and then the rest of it, and it needs to retain the directionality that's associated with that velocity vector. But the density, velocity, and dA, that's really just the volumetric flow rate multiplied by the density of the fluid. And so later on, when we talk about sign convention, we're going to need to be careful to retain the directionality of the first velocity, but not the second one. Because if we had, for example, some fluid flowing to the left, which would be a negative sign for the direction of the velocity, if we put the negative sign into both of those v's, then it would actually cancel out the directionality of it. So I just wanted to point out that really these last terms are just the volumetric flow rate. So then on the inside of the control volume term, we've got some change in volume multiplied by the density. And so again, that's the mass flow rate multiplied by velocity. So Reynolds transport theorem, we're saying that we could combine Reynolds transport theorem and the second law to say that the flow of this fluid through control surfaces, and there can be an accumulation of momentum inside of the control volume in some circumstances. We'll look at a video in just a moment that illustrates how you can accumulate momentum. But those two terms together can explain an imbalance in forces. Okay, so we're going to look at several cases through a series of examples of how fluid flow and momentum ties together. But first, let's talk about and then get rid of this idea of momentum accumulation, because it's kind of a specialized case that won't come into play in any of the problems that you solve in the homework and in the examples that we do. But you can have momentum accumulation through things like a flywheel, or in the case
Energy
of
storage flywheels have very high performance.
In the case of, for example, like a wind turbine. So, all right, so a similar thing applies to like hybrid cars, where as they're coasting towards a stoplight, the motor will switch off, and it will use the momentum of the vehicle to charge up the battery. Not a lot, I mean, but it's trying to recapture some of that same energy that, instead of just wasting it as heat when you apply the brakes, it's charging up the battery with the generator as you draw away some of the momentum as you come to the stop. So we have a lot of examples that there isn't any momentum being accumulated, either in a positive way or being drawn out of the system. And so most of the scenarios that we'll take a look at, they will have no momentum accumulation. And so we'll cancel out this term, and we'll say that the forces that we see due to fluids changing direction or a change in mass flow rate are going to be just due to the flow through the control surfaces. So the stationary structural parts and steady flow conditions, meaning that the flow rate isn't changing over time, allows us to say momentum accumulation is zero. And that's what we're going to see in our illustrations. So here is the then simplified version of the momentum equation after we cancel out the idea of accumulation in the control volume. Now we have to talk about what kind of forces we mean, because in the momentum equation, the sum of the forces are not the body forces. You know, body forces are those that can act at some distance away from the object in question without actually making any physical contact. And so there are gravitational forces, electrostatic and magnetic body forces, but what we're talking about instead are surface forces. So for instance, the hydrostatic force of water acting on a dam is a surface force. And another surface force are the momentum forces, where a fluid stream is coming in contact with a stationary body and applying a force to it. That's what we're going to be talking about with this sum of the forces in the equation. So just like in the Euler's equation, where you had to do a little bit of a translation depending on the direction of acceleration, in this case the momentum equation also requires a little bit of translation depending on how many streams in and out of the control surface you're observing. So this is showing that what we're saying for the sum of the forces is, if we're working in the x direction, for instance, then we would say the sum of the forces in the x direction are related to the flow out through the control surfaces multiplied by the velocity out in the x direction minus the flow in through the control surfaces and the velocity in the x direction. Now you could also apply this same general equation to other directions besides the x direction. You know, here's how it looks like in the y direction. You just simply change the velocity terms to be the component of the velocity in that direction. But you will notice that when we're talking about mass flow rates, we can't have a component of the mass flow rate in a certain direction. It's the entirety of the mass flow rate, but it's just the component of the velocity in a certain plane that we'll include for the velocity term. So sign convention is really important in problems like this. And I'm trying to always warn you of the mistakes that are most commonly made. And when it comes to the momentum equation, the biggest mistakes are using the wrong direction or not accounting for what direction streams are going in. So like we did before, we're going to assume that any flow to the right in the horizontal direction is positive x. So if a jet is going to the left, then that would be in the negative x direction. And then positive up is y direction, down would be negative y direction. It's also important to really be careful and meticulous in drawing the control surfaces and keeping track of whether a stream is in or out of the control surfaces. So you'll notice here in the momentum equation we have the outflow term first, and then you subtract out the inflow term following that. Now the way to interpret the left-hand side of that equation is going to be the sum of the forces required to hold the system steady. That's part of the sign convention as well. So we're going to be looking at stationary objects that are maybe being sprayed with a jet of water. And the way that we're going to do these calculations is we're going to be calculating the forces required to hold some system steady. So before we get into our first example, let's just get some practice with the sign convention, since that's so important. This first illustration is showing that if this is our control volume, and the outside edges of it is the control surface, then what's flowing in, the velocity would be positive. So if we had some numerical value for it, maybe 6 meters per second, then when we substitute the value here into the in term, then that would be a positive 6 meters per second. And the same with the out. Here, out, since it's to the right, then the sign of the out term is positive as well. Okay, now let's look at this one. We have both an x and a y, and we need to differentiate between the two. So if we're working in the x direction, the first stream is in, since it's going to the right, but the second stream is coming in from the left. And so you'll notice that we have a minus sign for that in 2 in the x direction. So if we were substituting that in, it's here because it's an inflow, but we'd have to put a negative value for the velocity since it's entering the control surfaces from the left. And then finally, in this example, why don't you in your notes follow the same pattern that I have till now. For each stream, identify whether it's in the x or the y, or it may be in both, and then identify whether it's positive or negative. All right, so let's consider stream 1. Okay, so stream 1, it's a velocity in, and so the velocity in at 1 is that in the x direction. Let's see, what's the convention I've been using? 1. Okay, so in the x direction, is it positive or negative? Positive, right, because it's pointing to the right. All right, so what about velocity in for stream 1 in the y direction? Negative, right, because it's pointing down. Good. All right, so stream 2. It's an in, and so velocity in for stream 2 in the x direction. So there's an x component because at least part of that arrow is going sideways. So is it positive or negative? Negative, good, because it's pointing to the left, so minus. And it's also going in, so velocity in for stream 2 in the y direction. Negative because it's pointing down. And now stream 3, the velocity out it's only going out. So velocity out for stream 3 in the x direction is to the right. So positive velocity out for stream 3 in the y direction, positive because it's up. All right. So as long as you give it a moment's thought, it's easy enough to see if it's in or out and if it's up or down versus left or right. But it's the sort of thing where sometimes you can make a mistake by just working too quickly through it and not identifying all of the streams in a situation. So the problem-solving approach that we're going to use in this chapter is, first of all, trying to identify where to draw the control surfaces and being sure to enclose the system of interest with the control volume. And then there are going to be situations where we may need to combine additional governing equations with the momentum approach. Like the first example I'm going to show you is a combination of Bernoulli's equation and the momentum. So we're going to have to, just by reading the problem statement, looking at the sketch, try and identify if there are other equations that fit in as well. It's a good idea to sketch the forces that are being described in the problem statement and draw a sketch of the entire system for that matter, and then look to make sure that there's no momentum accumulation, like that there's not a propeller of some sort inside of the control volume, there's no flywheel, because then that would change things, and then finally sketch momentum flow vectors. All right, so let's apply that with this first illustration of a balloon connected to a straw, and the straw is going on a string. I think you can tell pretty clearly what's happening here is, the balloon is pressurized air, and if you have an opening that is allowing the gases to escape in just one direction, then if this force wasn't applied, then the balloon would fly to the right and the string would kind of guide its path. But a force is being applied. So some force is being applied to hold the system steady. Now we just have this going in the x direction, so we don't have any y momentum that we have to keep track of here, just x. So the momentum equation in the x direction is provided there, and this is a simple case because there's only mass flow out. There isn't any mass flow in from this system. So the first thing we can do is draw the sketch and the boundaries that go around it. So we've got our balloon at the opening, and here's a control surface. The outgoing air will exit through the control surface, but the balloon itself stays inside of the control volume. Now, I mentioned before that we're going to have to use Bernoulli's equation in this case. And the given information in the problem statement, it says that we know the pressure inside the balloon. We know the pressure inside the balloon is 0.4 meters of H2O. And I don't think that that's a way that we've seen pressure expressed so far. We've seen kilopascals, and we've seen newtons per meter squared as a pressure measurement. But what do you think, how do you interpret here where it's saying the pressure inside the balloon is 0.4 meters of water? Equivalent to the depth. Yeah, so the pressure here, let's call that 1. So the pressure at 1 is the same as the pressure would be in some tank where you have a depth of 0.4 meters and the tank is 9810 newtons per meter cubed. So it's water. And so it's just basically saying apply the hydrostatic equation and you can know what the pressure at location 1 is. Now Bernoulli's equation says that we have an exchange in energy, that pressure is exchanged for velocity. And so P1 plus gamma Z1 plus density velocity 1 squared divided by 2 is equal to P2 plus gamma Z2 plus density V2 squared divided by 2. So here, location 2 is the gas that's coming out of the balloon opening. We want to know what that velocity is because that's what goes into the momentum equation. We also need to know the mass flow rate. And here in the problem statement, it's telling us the air density and also the nozzle diameter. So those are some important clues that you're going to need to be able to solve for the mass flow rate m dot. Okay, we have plenty of time, so I don't want to give away too many of the details here. I want you to think through this and see if you can find, first of all, what's the velocity of the gas that's coming out of that balloon. And then once you know that exit velocity, I think the next step is to find the force required to hold the system steady. In other words, what's this F that we have to apply so that the balloon actually doesn't start moving? So why is it that we're assuming the velocity at 1 is 0? It's inside the balloon, like maybe we can think of the balloon as shrinking from the outsides towards the inside. And so the air that's actually going out of the nozzle is, it's accelerating from inside the balloon. Maybe it's not exactly 0, but it's going to be gradually, very slowly moving towards the nozzle outlet. So that's why we say the velocity at 1 is 0. What about this jet that's coming out? Why have I assumed that the pressure at 2 is 0? It's just open to the atmosphere, right? And so the atmosphere that's surrounding the outside of the balloon has the same pressure as the air that's coming out of the balloon. So this pressure measurement that we had of 0.4 meters of water, that was a pressure measurement relative to the outside of the balloon. So it's just really the difference in pressure between the inside and the outside. So if we say the pressure of the jet coming out is 0, then pressure at 1 is what's causing that velocity at 2. So we cancel out the elevation terms since this is oriented such that 1 and 2 have the same elevation. And all that's left is we rearrange to find that the velocity is going 80.87 meters per second. Now, when we substitute that into the momentum term of the equation, we're going to have to account for the directionality of that. So that's to the left. The exit gas is going out to the left in the momentum term. So let's just get a preview of, I'm not going to show the whole answer quite yet, but we are going to be able to simplify the momentum equation because there's no flow coming in. There's just mass going out and a velocity going out. So this m dot, the mass flow rate out, needs to be a scalar, meaning that it's not going to have a negative sign ever. Mass flow rate is always a positive value. And so even though this gas stream is to the left and this V, we're going to say negative 80.87. For the mass flow rate out, it's going to be the density, area, and velocity, but we're not going to put a negative value in for that V because mass flow rate needs to be positive. All right, so the force required is negative 0.616 newtons. And there are a couple of different ways to indicate the directionality of the force. Like if I go back to the sketch that I drew, I had already shown that the force was to the left. So I could have said that the force is 0.616 newtons as shown. And so if I wrote 0.616 newtons in the direction shown, then that would mean look back at the figure and I'm trying to tell you that the force is to the left. Here I've put the negative sign here and I'm specifying this is the external force required to hold the system steady. So let's look at what's going on here. We calculate the mass flow rate with the density of the gas, that's the air, The cross-sectional area of the opening of the balloon, that was based on the 1 centimeter diameter that we've got. And then the velocity. And although the velocity is to the left, I didn't put the negative sign there because we always want mass flow rate to be a positive value. But we did preserve the directionality of the velocity here in the negative 80.87 meters per second because that is going to the left there. And so that's what makes the force a negative value as well. So this is relatively easy because there's only a single stream and it was an outflow but nothing coming in. Later on, I think in the second assignment that you'll have to do in Chapter 6, you're going to have multiple streams going in different directions, and so there will be a lot of accounting and keeping track of the in and the out just to make sure that we've got it all. Any questions on this one before we move on? All right, well that first video was so fun. Let's watch another one. Hoping that nobody blows up or falls down out of the sky, but this is called the flyboard air. It's a French invention. The first one was from...
When the first video of this invention appeared on the internet...
All right, so let's put our newfound momentum knowledge to good use here. Let's assume that the rider is 80 kilograms and that the board and the fuel together is 20 kilograms. You saw that he had a backpack with tubes coming out of it. One would assume that that's just a whole lot of fuel and just about nothing else. If we've got a fuel burn rate of 2 kilograms per minute, which, I don't know, I think I just pulled that number out of the ether. I don't think that's actually based on anything I read, but the fuel-to-air ratio, that is some reality there. For every 1 kilogram of fuel, then that means there's going to be 3.5 kilograms of air. Then what's the mass flow rate of the exhaust, and what jet velocity must be achieved? And so, in other words, let's assume that the forces that we're trying to calculate here are the sum of the forces in the y direction. And so we could draw a little sketch of the situation, and we've got the flyboard and the guy standing on it. Okay, stick figure. I should put a beret on him since he's French, but anyways. All right. Here is our control surfaces, and we want to find the sum of the forces in the y direction. And so what we know is that it's going to be the mass flow rate out multiplied by the velocity out in the y direction minus the mass flow rate in times the velocity in the y direction. And this is another situation where there's no mass flow coming in, but we do have mass coming out. And so the flyboard is pushing up as the gases are going down, and we want to know what's the mass flow rate of the exhaust with this burn rate and the fuel-to-air ratio, and then so based on that and how much thrust we want to achieve, then what jet velocity has to, what must be the velocity of these gases that are being directed downward. So you're going to convert this mass of the rider and the board from a mass into a force and use that on the left side of the equation.
Not miles. Meters. Let's convert to miles per hour.
So we need the mass flow rate in kilograms per second, and that's the mass of exhaust that's coming out through the control surface, and that's going to be the mixture of fuel and air together. So if we're told that it's every minute it's 2 kilograms of fuel, and that means that every minute it's going to be 9 kilograms of exhaust. So on a per second basis then, it's 0.15 kilograms per second of everything that's coming out of the bottom of that flyboard. Now, by the way, you'll notice that I said the best case scenario is that we assume that there's no mass coming in and no velocity coming in, because you'll notice here in the momentum equation, if we account for the fact that actually the air has to come from above in order for it to be able to go out the bottom, that's going to reduce a little bit of the thrust that it's able to generate. So if it's going up, for example, if he's gaining altitude, then the incoming air is going to be reducing the force ever so slightly. I mean, the relative velocity is going to be much lower, because as we see later, if this mass flow rate's pretty low to support 981 newtons of force, and if you've got that much force you're trying to generate with that little of a mass flow rate, then the gases have to be moving 6540 meters per second. So 6.5 kilometers every second? I mean, that seems unrealistically high, right, for the velocity of those exit gases. But, I mean, the math's the math. And so what it probably means is that the mass flow rate was probably higher than that. He's probably burning fuel at a higher rate than 2 kilograms per minute. So the flight times are probably really, really low. They said that he set a new world record for going about 2 kilometers. And so I guess maybe from that and estimating the speed, we could see how long the flight duration was. But 10 minutes?
Which doesn't seem right.
Yeah, it doesn't seem like you'd be able to hold enough fuel on your back for a 10-minute flight. But that's just a good illustration of the simplest kinds of applications of the momentum equation. Any questions on this example before we look at a couple of pictures here? Okay, there are 3 main types of problems we're going to solve in Chapter 6. And they fall into these categories of fluid jets. And so this illustration is showing if we have a stream of some fluid coming in, then you can look at that and see, since it's on rollers, it's going to have a tendency to move to the right if it isn't otherwise secured. And so this tether is going to develop some tension in it, because the concrete that's coming in would cause that container. It's going to apply a force to the container that would shift the container to the right if that tether wasn't there to hold it. And so these types of problems we'll look at the velocity of the mass flow, the velocity and the mass flow, to find out what the force is required to hold the system steady. So that's one type of the application problems that you'll be solving in Chapter 6. Another one has to do with vanes. And vanes like this redirect a fluid stream, but they don't necessarily change the mass flow rate or the velocity. Sometimes, depending on the problem statement, we'll assume that the velocity of the fluid as it exits contact with the vane maybe is a little bit slower than the velocity of the fluid as it's coming in. But in both of these cases, we'll follow the same approach of putting a control surface around the object of interest where there's a collision or an accumulation of fluid occurring. And then we're going to look at the stream of fluid that's coming in, the stream of fluid that's coming out, the direction of the velocities, the mass flow rates, and then try and look at the forces that arise. One of the tricky things is going to be in the problem statement, it will sometimes say what is the force required to hold the system steady, and then sometimes these problems will say what force is the liquid applying to the vane. So if I gave you a problem like that where it said, you know, we've got a jet of water that's intercepting this vane and it's being redirected in its direction, what force is the water applying to the vane? Well, in that case, it would be the equal and opposite of whatever you find according to the momentum equation. Because the momentum equation is saying it's an external force required to hold the system steady. So if you applied the momentum equation to the problem as it's shown here, that's basically like saying if I was applying some force, we can just tell by looking at it, I'd need to push on this vane to the left and downward in order to cause this liquid to change its direction. So that means the force of the liquid on the vane is to the right and upward. So pay special attention to what it's asking you to solve, because sometimes it'll just be that same sum of the forces that's on the left-hand side of the momentum equation, and sometimes it'll be the equal and opposite of that. The most complicated application of the momentum equation is going to be when we look at nozzles. And what makes that tricky is that we're going to have to account for not only the flow of the fluid and the mass flow rate and the velocity, but also when you analyze a part like this, and the pipe continues, not shown, but we are cutting the pipe with control surfaces, there is a pressure acting on the outside of the control surface that is, has an effect of an external force. And so we'll get into the details of that later, but I just wanted to show you these three broad categories of problem types to give you an idea of where things are heading. I would encourage you to get an early start on this homework. You've still got, let's see, where are we? There it is. You've got a week until it's due, but things are going to happen really quickly. That exam will sneak up on you, and things will pick up in the semester because projects are starting to get assigned, and Thanksgiving holidays getting closer. So getting an early start on this homework will help take the pressure off later on. So that's it for today. Hope you have a great weekend, and I'll see you next Tuesday.